We know Newton's second law, and we know acceleration, but how do these two equations relate? If we substitute change in velocity over change in time for acceleration, and then rearrange, we'll see that force is also equal to change in mass times velocity over time. This new equation shows us that force can be defined as change in momentum with respect to time. Well, what is momentum? Quantitatively speaking, momentum is just the mass times the velocity. This variable we usually use is p. Qualitatively, it's a bit harder to describe, but we all understand it. We all know that if there's a heavy object moving quickly, it's going to be difficult to stop. A lot harder to stop than a light object moving slowly. We all understand that moving objects have momentum. They want to continue moving. Momentum is associated with moving objects that have a mass, but so is kinetic energy. In fact, the formula for kinetic energy uses the same two variables as the formula for momentum. Since they're similar concepts, they're often confused, but it's important to understand the difference between the two. Recall that energy is the capacity for doing work. Kinetic energy is just another form of energy. It's typically measured in joules. Kinetic energy is a quadratic. If velocity doubles, kinetic energy quadruples. If velocity triples, kinetic energy is multiplied by 9. Energy is also a scalar quantity. Energy has several different forms, but momentum is strictly about moving bodies. It's a vector quantity. It's typically measured in kilogram meters per second. It's the quantity of motion of a moving body. It's how much a moving body wants to stay in motion. Another thing about momentum is that it's always conserved. This means that before and after any collision, the total momentum of all objects involved will be equal. For example, let's say we have a toy car. This toy car weighs half a kilogram. The toy car is traveling at 5 meters per second north. It collides with and joins a toy train in motion. Before the collision, the toy train was traveling 3 meters per second north, and it weighs 1 kilogram. The total momentum of the car before the collision is 0.5 kilograms times 5 meters per second, or 2.5 kilograms meters per second. The total momentum of the train before the collision is 1 kilogram times 3 meters per second, or 3 kilograms meters per second. If we add up the total momentum of both objects before the collision, we get 5.5 kilograms meters per second. Remember, momentum is conserved. So this will be the same value of the momentum of the joint body after the collision, which will be the car and the train moving together. Now, after the collision, we consider both toys one object because in this specific situation, they're traveling attached to each other and at the same speed. The total momentum will be 5.5 kilograms meters per second. The total mass will be 0.5 kilograms, the mass of the car, plus 1 kilogram, the mass of the train, so 1.5. If we rearrange, we can calculate that the speed of the joint body after the collision is around 3.7 meters per second.